next contribution is from Francis Robicheaux from Auburn University. And Francis will talk about ultracold plasmas probed by fluorescence.
Again, I would like to thank the organizers for inviting me to give a talk today. This has been a great workshop. What I'll talk about today is a project on looking at ultracold plasmas and using the fluorescence that comes from the plasma as a probe of what's going on inside the plasma. My collaborator in this project is Scott Bergeson, an experimentalist at BYU. And no, that's actually not right. Scott is really sort of the guy who had a lot of the ideas and was really pushing the project. Scott was sort of the big dog on this project. I'll be giving sort of a very theory-centric kind of picture of this, but Scott was the big guy on this. Let me start out with a slide that kind of describes the general setup and a little bit of the experimental details. As Steve mentioned, the idea is that you've cooled atoms in, say, a magneto-optic trap, and you use a pulse laser to ionize the atoms. And because you have control of the laser intensity, the laser frequency, you can control sort of the initial temperature of the electrons that were made in this first step, and the number of electrons and ions that you make in this step. And the electrons then get bound to the space charge for the ions that are sitting there. And you have sort of a plasma that ends up expanding because of this pressure that Steve mentioned in his talk. For the experimental details, this is a picture from this paper of what I presume an experiment looks like. It's bright and shiny, and that's about all I can really say about the experiment. So let me talk about, is there like a button that gives us better resolution that I can hit? Because it looked better than this.
CPU something.
Lab CPU?
Yeah, lab CPU.
Okay. Maybe that's not.
If it doesn't do anything, that's
Then it's dead. Okay. Well, it looked better before. So to give you guys an idea of sort of the relevant sizes of the parameters, this is something that Steve mentioned. The electron temperature is controlled by the laser frequency. The density is partly controlled by the density of the atoms in the MOT, but it's also controlled by the laser power. The more ionization you get, the higher the density is going to be. The initial ion temperature depends on the cooling that you did in the MOT and could be 10 microkelvin, 100 microkelvin, or more. Just to give you kind of a sense of the size of these things, if you're talking about a density of 10 to the 9 per cubic centimeter for the electrons, you're talking about basically an interparticle spacing of a few microns. And this is much smaller than the size of the plasma. A parameter that Steve mentioned is the Coulomb coupling parameter. One way to think of it is it's the potential energy divided by the kinetic energy. And this is very important because in some sense, if gamma is much less than 1, then sort of you have all these little potential features down here, but your energy is up here and you just kind of glide blithely over all of that stuff. When gamma is about 1 or so, then in some sense you have potential features that are about the same size as the energy that you have. So to kind of do any kind of motion, you sort of have to do it in a somewhat correlated way. And if gamma is really big, then you have these potential features and you're kind of sitting on the bottom. And then to actually move, you have to do a really complicated dance of many particles all moving at the same time. For charged plasmas, gamma of less than 1-ish sort of looks like a gas-ish. Gamma is bigger than 1, sort of look like liquids-ish. And gammas over about 100 sort of look solid like. So that kind of gives you sort of what these things might look like. If you have 100 Kelvin plasma, so easily tuning the temperature of the electrons, you can have this gamma go from easily something that sort of looks like a gas to something that's more correlated at the same density. Another important parameter to kind of keep in mind is sort of what an average electron speed might be. So even if you take like 10 Kelvin, you're talking about a couple tens of kilometers per second is sort of the velocity. And since the size of the plasmas are a few hundred microns or so, you're talking about times for the electron to kind of cross the plasma to be a few tens of nanoseconds. So the electrons inside the plasma are really kind of seeing the whole thing on a very short time scale. As Steve mentioned, there's a collision time that is in essence just a Coulomb cross-section in the square brackets, a velocity and a density to give you a rate. This logarithm thing is in essence the cutoff of the Coulomb scattering integral, and one way to think about it is sort of the minimum scattering angle that you're allowing. And for temperatures of 100 Kelvin and 10 to the 9, you're talking about thermalization times of tens of nanoseconds. So again, these kind of time scales for collisions are very, very fast. Now, the ion-electron thermalization time goes like the ratio of the mass of the ion to the electrons, and that's much, much longer. So in some sense, the electrons are bumping into all these ions, but typically they don't transfer huge amounts of energy to them. For the system that we're going to look at, recombination is going to be wildly important. So as Steve mentioned, that the three-body recombination goes like a constant times the density squared divided by temperature to the 9½ power. So even sort of relatively not huge-ish changes in the temperature results in fantastically big changes in the three-body recombination rate. And this is going to be important because when we're looking at this fluorescence, how are you going to get the fluorescence is first through recombination. And just as sort of a point of comparison, roughly for, say, 10 to the 9 per cubic centimeter, this kind of three-body recombination rate and sort of electron scattering rate, or the thermalization rate, are somewhat comparable. So I'd like to do a little blast from the past. Steve showed a little bit of this. This is a paper from almost 8 years or so ago now. And what they did was they measured the Rydberg atoms in a very cold plasma. And there's a couple of things that were interesting at the time. One thing was that the distribution of Rydberg states was kind of odd. There's another thing was that the time dependence of how many Rydberg states were detected as a function of time was also kind of odd because it decreased and then increased again. But the thing that I kind of want you to kind of see is that there was strange stuff at the time that the measured distribution, for example, gave more deeply bound atoms as the temperature decreased, whereas you would have expected it to do the opposite. There was all sorts of difficulties in understanding what was going on, and I think it was one of these workshops, like at ITAMP a long time ago, that Steve kind of showed these results, and everybody puzzled over it. And so we decided to get into the game and do some calculations. And this has sort of become a theme for, I guess, my approach to physics in recent times is that sort of thinking is highly overrated. And that what you should do is you should kind of just do the calculation and see what it gives. And a lot of times it turns out that the stuff that was sort of odd, that you were like, where did this all come from, just sort of falls out. And so when we kind of did these calculations, what we did, and sort of by standards like Thomas and Michel have going today, these were somewhat kind of crude calculations. We put in sort of the electron thermalization because that's important. The electrons don't start out in a thermal distribution, so how fast you get to a thermal distribution is important. We put in the ion motion. And wildly important was the coupling of the plasma and the Rydberg atoms. And that leads to heating that Steve mentioned and the more deeply bound atoms. But we just did it was all relatively simple stuff, rate equations for three-body recombination, all that stuff. And we got good agreement with what was measured by Tom and Steve for this, and we even made some predictions, like, for example, simulations show that the Coulomb coupling constant doesn't become larger than about 1/5 for these things, and that hadn't been seen except for like a few years later that came out. And I think actually in here we even said you might not really see any difference going from above to below threshold in any of the plasma parameters. So this, I'm really proud of this work, but I would like to now talk about the stuff that we recently did. It was published in PhysRev Letters last year, almost a year ago today, where instead of looking at the Rydberg atoms by like microwaves or state-selective field ionization, in essence, we're going to use fluorescence as a probe for what's going on. So if I don't want to go that way. So in this experiment, notice that in some sense the principal quantum numbers that were measured were from 55 up. And in the experiments that Steve mentioned, they were from like n equals 35 and up. So these are sort of the most weakly bound atoms that are being made in the plasma. And so the thing that Scott, this is sort of Scott's idea, he said, you know, I've got some experiments, and what the experiments are about is it's sort of the usual thing. We've got a mott. Well, I have a mott, he said to me, and I certainly don't have one. But Scott has a mott. Scott has a mott. And so he cools this little blue ball of atoms, and you ionize it with two lasers. This is calcium that this experiment is being done. It's a calcium mott. And you do the laser ionization just like you do in all of the previous ultracold plasma experiments that have been done before. But what we'll do now is look at the fluorescence. And the basic idea, well, let me show you. Well, yeah, let me say what the basic, why this might be interesting. Why it might be interesting is that, in essence, the fluorescence will be from a very low line state. And so now what you're doing is you're not looking at sort of the huge mass of population that's weakly bound. You're looking at sort of the very tail of the distribution that's managed to get to very, very deeply bound levels. And so this is going to, in some sense, give you a new insight into what's going on in the ultracold plasma, or at least a new tool to look at it. So what we're going to do, well, what Scott did was looked at the fluorescence that came out of this plasma as a function of time. And so this is sort of what it looked like. So just to kind of get you oriented, the calcium mott, so sort of the cooling transition, I think, was the 4s squared to 4s4p at 423 nanometers. So you cool here, and then you have a pulse laser at 390 nanometers that takes you above the lowest threshold so that you make ions. And that will leave the calcium in the 4s state. So the 4p threshold is way, way high compared to this. So everything is being left in the 4s state when you ionize. And what the signal will be, so he had a little filter looking at the fluorescence. The signal isn't just all light coming from the plasma. It's just light of essentially 410 nanometers. And that's the 4s 6f to 3D 4s transition. So what, in some sense, he's probing, since this is a really fast transition, he's just probing the population in the 4s 6f state, so way, way down in the tail of the distribution. Okay. So to give you a little credence to sort of that I actually sort of know what I'm talking about, this is a comparison between the experiments are the black dots and the calculations are these red lines. For initial plasma made at about 57 Kelvin, the fluorescence as a function of time going from about 0 to 40 nanoseconds kind of goes up, it comes down. The calculations and experiments are in decent agreement. Before kind of going into detail on this, I would just like to mention a couple of things. So this is just sort of 3 slices, but there's several parameters that really depend on both the temperature of the initial plasma and the initial density. So for example, how fast the plasma, this fluorescent signal rises at early times really depends on the temperature and the density. You change the temperature and density, that changes in an easily measurable qualitative way. The peak position, so where in time this fluorescence peaks, depends on the density and the temperature. And it changes qualitatively as you change these things. The overall amount of fluorescence changes because how much recombination you get, and all that depends on the density and the temperature. And how fast this thing decays away, how fast this fluorescence signal decays away, also depends on this. Right? Now, Scott, well, let's see. So here was the original idea. I don't know if I actually said what the idea was. So I'm glad I have this up here because now it reminds me. Here's what the original idea that Scott had, is that when you do recombination, you really are recombining into really weakly bound states. To get down into this low state that's fluorescing, you have to do a whole bunch of collisions. And all of this is going to depend on the density and the temperature in a complicated way. So to get this right, you have this long chain of events to see this thing. So to get this right, we're going to really be having a strong constraint on both the atomic physics and plasma physics. That, in some sense, a lot of stuff has to be right to get this right. Right? So that's the idea. So just kind of to say where these features come from, this sort of fast initial rise is just coming from the fact that you have to have recombination and then collisions to get you down. So you don't start off with a signal at t equals 0 because you don't have any atoms at t equals 0. It takes time to kind of have stuff go in and knock them down to a low enough state to fluoresce. And so this bit right here is coming from sort of the recombination and collisions. This decay is coming from two effects. One effect is that as the plasma expands, the density is dropping, and so collisions to knock the atoms into low states takes longer and longer. But the other thing is that the plasma is expanding, and he's just looking at a little focal spot with the detector, so he's just detecting in a small volume, and that sort of the number of atoms inside the volume is dropping. And that's actually the bigger effect here. But that's sort of generically what's going on. And I talk real fast, I smile, and I'm sort of short, so nobody's really alarmed, but actually one of these things is wrong. All right? So I'll tell you which one in a second. So Scott kind of knows that I'm sort of old battle-tested theorist, and given something that looks like this and enough free parameters, I can easily fit it. Without any real trouble. I wouldn't even break out in a sweat. So he said, let's go in and look at one very specific thing very carefully, and I'm not going to allow you any wiggle room. And that is this very early, I want to go back, this very early slope. So just the first microsecond, what's going on? Let's just only look at that. So what's happening in the first microsecond? And so he did some measurements at different temperatures and at 3 different densities. And you might not be able to see this, but what he did was he took the fluorescence signal and divided it by the density cubed for the 57 Kelvin and 30 Kelvin, and by density essentially squared for the half Kelvin initial plasma. And so at high temperature, the signal is proportional to density cubed. It's pretty much linear as far as you could tell, right? So this should be an easy thing that we can get right, is to say, what is going on at early times? Why does it go like density cubed? And this is very simple to do. You know that 3-body recombination goes like density squared. You know like the total number of ions and electrons in your system goes like the density. And you know that the collision rate to knock you down to low enough states to give you fluorescence goes like the density. So the signal should go like density to the 4th power. Furthermore, if you're doing this as 2 steps, none of which start out populated, so if you're saying I recombine and then I scatter down, the time dependence shouldn't go linearly with time, it should go quadratically with time, right? And that's also not here. So as it probably wouldn't come to us as a surprise to most of you, but I called up Scott and I said, the experiment must not be working. it must be wrong, go back and try again. In retrospect, I would like to think that I did this very diplomatically in a way that I could wiggle out of later, but I kind of fear I probably didn't. But anyway, so I told Scott it must be wrong, and he went away and he came back and he's like, no, while the overall density is not that well known, the relative density from each plasma is well known. I didn't say it, but the spread in densities here is a factor of 4, and you cube 4, you're talking about 64. So there's the actual signals are varied over a huge range, and they lay just right on top of each other. And I was just worried about these guys. I mean, I'm not even thinking about this up here, but these guys, it's got to be right. So I went back and I said, all right, I'm going to actually, thinking has failed me so often in the past, I'm just going to do the calculations. So I rolled out my old codes, I started cranking, and out came the fluorescence signal, and the fluorescence signal was proportional to density of the 4th power and time squared. And so I went in and fiddled with the scattering rates, the 3-body recombination rates, the fluorescence, all of these things, and nothing worked. It all behaved exactly the same. And so I really started getting desperate, and I started putting in the actual quantum decay rates from the individual n levels down in L. So I put it all in for hydrogen, and it made no difference. And so Scott asked me sort of, why are you doing hydrogen for the radiative decay rates? And I said, well, because it doesn't matter. You're talking about Rydberg states that these things are decaying from. They're all basically high L, and the difference between hydrogen and the other atoms are only at low L. So I was like, well, to please you, I'll do it for potassium. I have those potentials. It's easy to calculate. I did it for potassium, bang on exactly the same that I had before. It wasn't, the calculations did not agree with the experiments. And so after an embarrassingly long time, it all of a sudden hit me that calcium is not an alkali atom. That calcium is an alkaline earth atom. And the importance about the difference, so going from hydrogen to potassium made no difference. Going from potassium to calcium turns out to make all the difference in the world. And the reason is this lovely paper from about 30 years ago, where they look at the spectrum of the J equals 2 levels in calcium. And sitting right in the region near the threshold was a big old whomping doubly excited state that's mixing with these guys. And the reason why this is different is the reason why sort of Rydberg states don't kind of talk to the ground state so well is because all the oscillator strength is used up just talking to the nearest 2 Rydberg states or so. If you have some 3D squared mixed in, that bit talks directly to very low bound states. So it turns out that going and putting in this extra bit of oscillator strength is huge, especially since this is a J equals 2, and he was in essence looking from fluorescence from an F state. So when you go in and you put in this extra bit right here into the dipole, you find really a sort of perfect match that the signal now, when I calculate it, goes like density cubed and goes like time, just like is seen in the experiment. And the reason for the difference is 3-body recombination is proportional to density squared. The number of ions is proportional to density. You don't need to scatter down to low levels to actually start fluorescing. If you don't put in the doubly excited state, though, it's really a mess. It just doesn't work. And this is an important thing. I mean, there's actually something, it's like, in some sense, not all Rydberg states are the same. And there's actually a qualitative difference here in that when you have something like a doubly excited state mix in with your Rydberg states, it makes a big difference. And just the other week, I kind of mentioned this to Tom Gallagher, and Tom's response, I think this is verbatim, Tom's response was, "Duh, I thought you knew that." Like, oh, yeah, okay. But why did it take so long to actually think of this? I mean, first off, I actually blame it on my poor training as a postdoc. when I was a postdoc, I had to calculate the spectra for all these like really complicated atoms, you know, scandium, this stuff. I even calculate stuff for things that don't even exist, but not once did I calculate for calcium. But anyway, what's that? I should have known. But the thing is that I should have known because and all of these actually have the same kind of property. It's one of these things I knew but didn't know, I guess, well enough to actually apply it to a different system. We've seen this in almost all Rydberg states. It's like whenever you have these states embedded in the continuum or embedded in the Rydberg series, it qualitatively changes things. Anyway, the last thing I'd like to talk about is what's going on here. Is at very low temperatures, the signal goes like density squared. Where did that come from? And it turns out that this is a very interesting effect, and it's kind of hard to see. But what I did was in the calculation, so this is something that I could easily do in the calculation, but couldn't be done in the experiment, is in some sense I took the amount of 3D squared stuff that got into the 6F state as a function of time from 0 to 1 microsecond. And it turns out that basically at long time scales like the density. And I also looked at the amount that actually needs to scatter down. And that scales like density cubed. And it turns out that this bit right here is not really sort of a pure scaling of one thing or the other, but it's really kind of a compromised position between this kind of behavior and this kind of behavior. So it really was sort of, in the end, like Scott's vision that to get this guy right, you actually kind of had this to get these very disparate parts of the recombined population correct to get this right. So I don't really have time. We also are now doing a different kind of experiment, but I think my time is up. So let me just kind of summarize. So we've looked at this fluorescence from come back. We looked at the fluorescence from ultracold plasmas. It seems that even at these very low temperatures and these very extreme ends of the distribution, that atomic physics plus standard plasma physics still seems to be explaining everything. But you really are looking at different parts of the distribution. And if we had been using calcium or just a different state, we would have seen a completely different kind of dependence. So this is actually kind of a neat thing, is that maybe using, instead of calcium, maybe using magnesium would have given something that looked quite different. So let me stop here. Thank you for your attention.
Yes,
Since you're looking at fluorescence from low-lying states, are there any processes involving the residual ground state atoms that could be important or could provide other diagnostics? You have some residual fraction of atoms that are not excited and participating in the plasma.
Yeah, Steve kind of mentioned this, is that those cross-sections tend to be sort of atomic sized. And so they tend to not be playing a huge role in the plasmas where the size scale is more like micron size. So
still looking at fluorescence from low-lying levels, so there are no processes involving those atoms that could...
No, there is some scattering down. So like from n equals, so when you go to these dense cold plasmas initially, then all the time developments that are there and scattering do play a role, but it only plays a role down to about n equals 20-ish, 18-ish, and then sort of radiative cascades take over after that and brings you down much faster than anything else.
Yeah.
So I have a question about, so the state that's being measured, the fluorescence from, that the upper state has a similar problem to the continuum in that it's in a real atom, not hydrogen, and the radial matrix elements can be all over the map for that particular state. There's things that feed it. So how it's actually getting there depends a lot on the atom too, right?
That's right.
So
yeah.
What you learn out of this is not necessarily anything, say, you're not really getting systematic by looking at what's coming out of one state, because you could get a completely different dependence even out of the same atom.
That's right.
You get a different.
Absolutely. So if instead of looking at the 4s6f, he was looking at the 4s6s to like 4s4p transition, you would probably seen a completely different fluorescence signal. But that's actually, I would say that's, so taking a problem turning it into a strength, I would say that that's actually kind of a neat thing, because now you haven't changed any of the plasma dynamics, but you're now looking at a different part of the population distribution, because you had to get there by a different path.
Chris?
One thing I was wondering if you have a feeling for how this goes. I would think that there's a range of binding energies of this perturbing doubly excited states that's relevant. And like if you had much lower density plasma or much lower temperatures, maybe it would be much higher ends way above the perturber. And then you'd go back to the end.
Absolutely. And actually how we kind of found, how this ended up getting found was, is sort of the standard sort of theorist trick, is that desperation just set in, and we just started plotting everything. And then we kind of noticed that in the calculation sort of states 25, 30, 30. So I was plotting like the time dependence of how much population was in states by like 5s or something, all the way up to like 100. And it was like only like in this small range, it turned out it scaled like density cubed in time. And if you went down and looked at 15 to 20, it behaved differently. You went from 40 to 45, it behaved differently. Absolutely. So it was just looking at that sort of small slice.
There are any more questions? Okay, if not, let's thank Francis again.